AP Chemistry, Unit 1, Chapter 3, and there's a lot here, so I'm going to try to go over it as fast as I can so I'm not using up a lot of your time, but feel free to skip ahead of the video to different places that you need the help with. But I'll just go ahead and start with the beginning. The average atomic mass of an element, you need to be able to do that, the atomic mass value for that each isotope as well as the percent abundance. Number 2 is a really good example of that because we have the percent abundance of chlorine 35 and the percent abundance of chlorine 37, and then their actual masses. Now, the reason why these masses in atomic mass units is a little bit different than the average, or excuse me, the mass number of the isotope is beyond what we study right now. So we're not going to worry about that. Just understand that this is the mass that you need to use with this percentage. So it looks like this. 0.7553. Remember, ladies and gentlemen, anytime you deal with percentages and do math with them, you have to turn them into decimals. This will be multiplied then the 34.968. We're going to add that then. The other one, 0.2447 times 36.968. That's going to get us our average atomic mass, and this is the method that you use when you're dealing with anything that has percent abundances here and there. So I guess the really important thing here is that the percent abundance can skew the average. So since we have more of the 35 variety of the chlorine isotope, the average is going to be skewed closer towards that value. And it does turn out that the average for chlorine is going to be 35.45 for the average, which is closer to 35 than it is to 37. So this is isotope 35 and this is isotope 37. A really common question for this would be like, given lithium that has the average atomic mass of 6.94, and we have two isotopes of lithium. One isotope is lithium 7 and one isotope is lithium 6. Which isotope is there a larger quantity of? And it's going to be lithium 7. Because we have the average closer to that value. Because if we had equal values of these, the average would be 6.5, right? Oops, which is not the case. Get rid of that. All right, that was a lot. Number 3, determine or define mole, and what does it have in common with things like pairs, dozens, or gross, and what does Avogadro's number represent? So a mole is going to be a counting unit. And it's like these things because they are also counting units. A dozen is equal to 12. A pair is 2. A gross is 144. Or a gross is a dozen. So a mole is just another counting unit, and 1 mole is equal to then 6.022 times 10 to the 23rd. And this here is called Avogadro's number. And just to help you remember this, that is what I named my cat. My cat has the name Avogadro. We call her Avi. Who cares? All right, number 4. How many atoms are there in 5.1 moles of sulfur? So when we look at a mole, and we're doing these what we call simple conversion problems, we can go 2 directions. We can go to things, or we can go to mass. Mostly in chemistry, we live in this region right here, moles and mass. We don't often get into things, and kind of the point of having moles is so that we don't have to deal with things, because that's too cumbersome. Now that being said, we still do it from time to time, and things would be stuff like atoms, molecules, formula units, and other things like that. So we can convert into those using Avogadro's number. So we have our moles of sulfur, and we're looking for atoms, so we can go 5.1 moles of sulfur. 1 mole of sulfur, 6.022 times 10 to the 23rd. Those go away. And we end up with 30 times 10 to the 23rd ish. 5.1 times 6.022 times 10 to the 23rd. Got my calculator out. I'm doing that math right now. We end up with 3.07 times 10 to the 24th atoms of sulfur. All right. Let's do one more before we get a new page. We have 6.00 times 10 to the 9th atoms of cobalt. So this is number 4. Here's number 5. So we have 6.00 times 10 to the 19th. 19th times 9th atoms of cobalt. Looking for moles. So we're just going to go backwards. Here's our mole on the top. And our Avogadro's number on the bottom this time. So we end up with a really small number. Oh, 9.97 times 10 to the minus 15th moles. There you go. All right. Number 6. Grams of gold. So this is the normal conversion that we do. This is the one that we do over and over again. So
please call the office.
Sorry about that. So hopefully you don't need this one, but I'm going to do it for you anyway. 15.3 moles of gold. 1 mole of gold is 197 grams. Gold. Cancel. Cancel. 15.3 times 197 gets us a large number, 3014 grams of gold. Number 7, which contains a greater number of atoms, 1.1 grams of hydrogen or 14.7 grams of chromium, and justify your answer. I'm not going to do calculations, but I'll show you what the justification is. So if we go to the periodic table, hydrogen has a molecular mass of 1.01 grams per mole. So that's the mass in 1 mole. So if you have 1 gram of hydrogen, you have 6.022 times 10 to the 23rd atoms of it, because it's 1 mole. And then chromium is going to be much larger, 52 grams per mole. So each individual atom of chromium weighs significantly more, which means you need a much larger mass in order to get the same quantity of chromium atoms as you would of the hydrogen atoms. So if you have 1.10 grams of the hydrogen, you have something that is greater than 1 mole. If you have 14.7 grams of chromium, even though that's a significantly larger number than the grams of hydrogen, you're going to end up with something that's much less than a mole. So that's your justification. You have a larger number of atoms here because you have more than a mole. And we know the mole is 6.02 times 10 to the 23rd, less than that value here, because it's a much smaller number than our 52. All right. Number 8, molecular mass. So these are straightforward as long as you know what molecular mass means, and that's going to be the sum of all the different pieces. So we have sulfur, which is 32 grams per mole. We have oxygen, which is 16 grams per mole. We're going to multiply this by 3 because there's 3 of them. We're going to add all of these together. 32 plus 48 is going to be 80. Is that right? Grams per mole. Yeah, I think so. So there you go. I'm not going to show the rest. Calculate the molar mass of a compound there. So this is like if you don't know the chemical formula, but you're doing mass. Excuse me, you're doing actually data collection. You get those two different pieces. Here's our number 9. So we end up with grams per mole is the definition of molar mass. So in order to figure out molecular mass, you need the mass, you need the moles. Just divide. So we have 152 grams divided by 0.372 moles gets us a big number, 408.6 grams per mole. Now this is not an element. At least it's not one that we have in the periodic table. It's going to be some kind of molecular mass of a compound. So we can't go to the periodic table and figure out what this is. We just have the molecular mass, which is that guy there. Number 10, in order to figure out the empirical formula and molecular, or what do you need to determine the molecular formula? You need the molecular mass. For example, if we had an empirical formula of CH4 and a molecular mass of 48 grams per mole, that would mean that the molecular formula is going to be C3H12, because C3H12 is equal to 48 grams per mole, where CH4 is only equal to 16 grams per mole. So you need the molecular mass to figure that out. All right, let's get a new page here. Number 11. Tin exists in Earth's crust as tin oxide. Calculate the percent composition by mass of tin and oxygen in that thing. So percent by mass, percent of anything is the part divided by the whole. So we're going to take the mass of the tin and divide it by the mass of the tin oxide. We're going to take the mass of the oxygen and divide it by the mass of the tin oxide. Oops. We'll end up with our values. The mass of the tin is going to be one of the periodic table here, 118.7. Mass of tin oxide, 1187. Plus 16 plus 16. So 150. Same thing here. This is 32. Each oxygen is 13, so there's 32. 150.7. We can get our percents. So I'll put those down here. 118.7 divided by that guy there is 78.7. Where do you say that? 78.7%. Means that that's going to be 32 divided by 150.7. 21.2%. I think I rounded this wrong. I think it should be 8. So let's get that guy. There you go. All right. Number 12, cinnamic alcohol. So this is cinnamon. Has the molecular formula C9H10O. Calculate the percent composition of each of those and how many molecules are there. You know what? This is a review of the different things up here, so I'm not going to do them right here. The answers to these, though, are on the website. Let's see if I can show you that. There it is. So chapters 1 through 3. And here are the answers, so you can look at them there. So I'm not gonna do that one here. All right. Allicin is the compound responsible for the characteristic smell of garlic. Analysis gives you this percentage and the rest oxygen. Calculate the empirical formula. Calculate the molar mass. Or given the molar mass, calculate its molecular formula. So we've kind of already practiced this earlier, but let's go ahead and go through this entire problem. Remember that the empirical formula is the lowest mole ratio, lowest whole number mole ratio of the different elements in the chemical compound. So we need to get these things into moles. And since they're percentages, we can go ahead and convert those into masses, 44.4 grams. Now, the reason we can do that is because it doesn't give us a total sample size. If it did, we could then figure out what 44.4% of that sample size is the carbon and start with that mass. But since there's no sample size given, let's just assume that there's 100 grams because it really doesn't matter, and we can make the math easier. So here's what I'm saying. It doesn't matter what mass you choose for the sample size, your answer is going to come out the same. So if we choose 100 grams, it makes it easier on ourselves because that gives us the sample size of percentage equaling mass. So there is carbon, 1 mole. Carbon is 12 grams. Carbon. Hydrogen, 6.21 grams. Hydrogen. And then we have sulfur, 39.5 grams sulfur. 1 mole of sulfur is 32 grams sulfur. And we can't forget oxygen. 44, we gotta figure out the final percentage because it has to equal 100, right? 44.4 plus 6.21 plus 39.5 gets us 90.11%. So 100 minus that gets us 9.89 grams of oxygen. Gonna do the math here. I'll be quiet for a little bit. All right, so this is 0 here. Oh, bummer. Zero. This is our mole ratio right now between the guys. In this chemical compound, we have 3.7 moles to 6.21 moles to 1.23 to 0.62. What we need to do is get them into whole numbers. In order to do that, we're going to divide everything by the smallest one. That maintains the ratio and also gets us to whole numbers, because if we take 0.62 divided by 0.62, we end up with whole number 1. Due to each thing, we maintain the ratio. 1.23. Yeah, 2 figures. 10. I should say that right now in the calculator I'm getting numbers that aren't quite whole numbers. Like this was 5.968. Now, since we know they have to be whole numbers and this data is gathered experimentally, the values are going to be slightly off. So we can round to whole numbers. When we can't round to whole numbers is when we have halves. And we've done problems like that in class. So that becomes a whole number of 6. So our empirical formula is equal to C6H10 S2O. And we write it in order of how the elements were given to us in the problem. It's always written that way so your chemical formula comes out correct. So if we add all of this up, we end up with, let's see, 12 times 6 plus 10 plus 64 plus 16, 162. Now, when I'm talking to myself there, I'm just talking out loud of what the values are for the periodic table. So I've done this so often. I know that carbon is 12, I know hydrogen is 1, so there's 10. I know sulfur is 32 and oxygen is 16, so I can go ahead and do that in my head. Now, letter B says, if the molecular mass is 162 grams per mole, what's the molecular formula? Well, just so happens to be the exact same thing as the empirical formula, because the empirical formula has that molecular mass. All right, let's go on. Get a new page up here. And now we're getting into some other stuff. Let's see. Let me read through this. Like I said, guys, I'm going over this for the first time since last year, so a lot of times I have to read through things as well and figure out what's going on. So let's see. Why must a chemical reaction be balanced? And that is because in order to do so, it obeys the law of conservation of mass. And so if we want to do an example here, number 14, we could do the simple combustion of hydrogen plus oxygen makes water. If we look at this, the law of conservation of mass says that we can't create and we can't destroy matter. So if we look at how many hydrogens we have on the reactant side, we have to have the same number on the product side. 2 and 2, we're good. Oxygen, though, we have 2 atoms or 2 moles of oxygen, 1 on the product side. It looks as though we destroyed matter. We cannot do this. That changes the chemical formula of the product, and it's not allowed. So instead, we have to give it in packages. So I can say that I produce 2, whoops. Should I leave that there? Now let's erase it. Two water molecules. That gets me my 2 oxygens. 2 oxygens. Now that gives me 4 hydrogens. Put a 2 out front here. And so now it's balanced. It obeys the law of conservation of mass. That's what we need in chemistry. All right, number 15. Symbols of liquid, gas, solid, and aqueous. Here's liquid. There's gas. There's solid. There's aqueous. That's 15. 16. Silicon tetrachloride can be repaired by heating that stuff. In one reaction, we have that much produced of the silicon tetrachloride. How many moles of each reactant were used? So this gets us into our stoichiometry. Remember, the stoichiometry is a way that we can compare one thing in a chemical reaction to another thing in the chemical reaction. And this is done through the mole ratio. So I'm going to rewrite this. I'm going to leave off the states of matter. Silicon plus chlorine makes silicon tetrachloride. So we have 1 and 1. 1 mole of silicon, 1 mole of silicon tetrachloride. If there isn't a coefficient there, it's assumed. So we have 1 mole of silicon to 2 moles of chlorine to 1 mole of silicon tetrachloride. And that carries through. So we're looking at each reaction or each reactant if we had a certain amount of the silicon tetrachloride. So let's play around with this rather than using the actual value. Let's just kind of look at this. It's a 1 to 2 to 1 ratio. So if I had 2 moles of silicon, I'd take 4 moles of chlorine and I'd produce 2 moles of silicon tetrachloride. If I had a half a mole of silicon, I'd need 1 mole of chlorine and I'd produce a half a mole of the silicon tetrachloride. That ratio is maintained, and that's what allows us to compare one thing in a chemical reaction to another thing in the chemical reaction. So we're looking at the silicon tetrachloride here. We have 0.507 moles of the silicon tetrachloride. And it's simple enough to do some math in your head and figure out what it should be. Looks like it's going to be just over 1. But this is how we show the math. Using dimensional analysis, moles of silicon tetrachloride, moles of silicon, there's 1 to 1. It's going to be the same. And then we can go on to the next one, the chlorine. That's a 1 to 2 ratio. Still 1 mole here. 2 moles here. And there's our answer. We're just doing the mole ratio step here. This is something that isn't done really in real chemistry. It's just practicing the concept to make sure you understand what that mole ratio does for us. In real chemistry stuff, we deal with masses and volumes and volumes of liquids, volumes of gases, but we don't really work in moles. We just use moles to get from one thing to another. Alright, so now we're on to 17. I'm going to do 17 and I'm going to take a break and then we'll get a different video for the other ones. Ammonia. Ammonia is a really important chemical a chemical in agriculture because it allows us to produce the yields of crops that we do, and so without it, we'd have a much lower number of a lower yield than we would with it. So we need to be able to produce it, and it's produced through this process of reacting hydrogen and nitrogen gas to make it. So if we have this reaction here and 6 moles of ammonia produced, we can figure out how many moles of each of them were used to produce that much ammonia. So again, we're going to start here with the given information, 6.0 moles of ammonia. This is, hold on, let me start over here. Number 17, 6.00 moles of ammonia. Two moles ammonia, 1 mole hydrogen. That's the first problem. We're solving for hydrogen. Let's do the next one. 6.00 moles of the ammonia. 2 moles ammonia. 3 moles of the hydrogen. Is this thing balanced correctly? Yeah, okay. Those go away. So this 2 comes from the coefficient 2 here, and then coefficient of hydrogen, or excuse me, of, oh, I did these backwards, didn't I? So this is going to be the hydrogen up here. That needs to be the 3. And then this guy here is going to be our 1. Sorry. Oh, no, that's the problem, is I just did the same problem twice. Sorry, guys. This is why I'm going to take a break after this problem. So here's the 3 moles of hydrogen, doing the hydrogen. And then over here we have to do the nitrogen. So let me go ahead and fix this. This goes away. This is the nitrogen. There. And we get our answers. 6 times 3 divided by 2. 9. It's going to be 3. All right, so that is the beginning of chapter 3, up to stoichiometry basically, and then I'll go through the rest of the stoichiometry problems here in another video.